Dr. Atchison here, and we are going to do a hand calculation for complex ANOVA. So this is a one-way ANOVA for repeated measures. Okay, so just a little bit of a recap, and when carrying out an independent group's ANOVA, we're going to figure out this F ratio that has two different estimates of variance. It has our between group variance estimate, that is our treatment effect plus the differences due to chance and individual difference. And it has our within group variance estimate as well, which is our differences due to chance and individual differences. So this is what it looked like in our one-way ANOVA. The problem is, and so what we get with our F ratio is treatment effects, differences due to chance over differences due to chance. And those differences due to chance essentially kind of cancel each other out. Not really. But that gives us an estimate of the variance that's due to this treatment effect. The problem is with the repeated measures ANOVA, that numerator in the F ratio includes those systematic differences that we're interested in that are caused by treatments, and it includes those unsystematic differences, but they're reduced because we have the same individuals in all treatments. So we don't have individual differences here. No individual differences are found in the numerator. The problem is the formulas that we have to calculate the denominator, when we calculate mean squared within, which is what we've been doing in the one-way ANOVA, that gets calculated with as if there's individual differences. But the problem is there was never any individual differences. So what we have to do is we have to quantify this effect of individual differences, and we'll do that by calculating sums of squared between subjects. And then we have to subtract it from the sums of squared within to equal our sums of squared error, which is this error or this residual term that we're talking about here. Okay, so let's get into the study, the practice problem. And I really love puns. Me and my family are very punny. Ha ha ha. Anyways, so the next one is actually about puns and how when you get sleepier, do you come up with more puns? And so I thought it'd be fun to start with some puns. So I have the necessarily qualifications. Your qualifications are completely irrelevant. Don't listen to him. He's lying. This arguing is becoming unbearable. Indeed, it's making my voice hoarse. Hoarse, please. When did you ever say something smart? Don't worry, I'll wait. Ouch. Awkward. I'm out of here. You're all giraffing me crazy. So anyways, the idea is, behind this next study, is while we're getting tired, do we have more punish associations from a list of 100 words? So this was actually a real study that was done in 1889 and then was adapted in 1999. That looked at these two things. So they measured in this adaptation, they measured 5 people, and they measured them at 9 p.m., midnight, 3 a.m., and 6 a.m., okay? And so what we have here is we have repeated measures because we are repeatedly measuring person 1, person 2, person 3, or person 1 is getting repeatedly measured 4 times, person 4 is being measured 4 times, etc., etc. So what we have here is a repeated measures design with a subject size of 5. And these are our means for each time period. So for each condition, for 9 p.m., we have a mean of 9. For midnight, we have a mean of 15, 17, and 27. And what we're trying to figure out is, are there more puns kind of as the night goes on? Are there differences between these 3 groups? Okay, so since so much of repeated measures ANOVA is like one-way ANOVA, in that first step where we calculate our sums of squared total, our sums of squared between treatments, and our sums of squared within treatments, I'm not going to go back and do that here. We've already been given this data. If you're not familiar or you're not comfortable doing that, please take a pause, practice it, do the sums of squared for each of those, make sure they match up with what I have here. Go back and watch the other videos if you're still struggling with that step 1, but hopefully to a point right now that we're not struggling with step 1, so we can really focus on the next step. So this is what we've been given. We've been given our means, we've been given our sums of squared total, our sums of squared between treatments, and our sums of squared within treatments. Okay, we still are going to calculate all of the degrees of freedom from this step. Okay, so what we have here is we have the degrees of freedom. We said that there was a total of 5 people. So we have a degrees of freedom total of, excuse me, we have a 20 is our n, okay? Because we're calculating this just as we would if this was a one-way ANOVA. We're treating the data as if it was a one-way ANOVA. Our n is the number of scores that we have. Well, we have 4 levels and we have 5 people. That equals 20 scores. So this is going to be our degrees of freedom total, okay? So 20 minus 1 is equal to 19. Degrees of freedom within treatment is we're still doing these 3 like we would a one-way ANOVA. So we have 5 scores in each of the 4 treatments. So we have degrees of freedom 4 for each of them. And again, there are 4 different ones. Is equal to 16. Our degrees of freedom between treatments, again, we have 4 levels. Those 4 times minus 1 is equal to 3. Now here is where we're going to get into, when we get to degrees of freedom between subjects, this is where we're getting into our step 2. This is where we're starting to look at it differently, okay? So now it's saying, well, how many actual subjects do you have? Well, I actually only have 5 subjects. So my degrees of freedom between treatments is 4. And the degrees of freedom error is saying, okay, well, you told me up here before in degrees of freedom within treatments that you had 16, but because you really have less subjects than that, let's calculate that out. Let's get that error term out. So we'll take our 16 minus our 4 and we'll get 12. Okay, so the next step we're going to do is we're going to calculate that person total, okay? That person total, remember, is just like we've done before where we calculated down and we calculated a T for 9, for midnight, for 3 a.m., for 6 a.m. Here we're going to calculate a P, which is a person total. So just as we calculated a T for the columns, we're going to calculate a P for the rows. If you start thinking about this P versus T as columns and rows now, you'll be ahead of the game in 2-factor ANOVAs. So here is our P, 8 plus 22 plus 24 plus 34 is equal to 88. And we'll do the same thing for the next ones. And just add all those values together. And so these are our person totals, okay? And again, we just added that by adding each score from each person together. So here are those values again, but what's our G? We didn't copy that. You weren't given that. You were given your sums of squared, all your sums of squared from the first one, but you weren't given that. Now, granted, that was used in calculating, but all we're going to do is we're going to add all these person totals together. When we add all those persons totals together, we get 340. Now, if you were to have gone back and actually calculated those T's, you would get the exact same number. The sum of the T's is equal to the sum of the P's. And the reason the sum of the T's is equal to the sum of the P's is because all you're doing is it's the sum of all of the scores is all it is. So that's why all of these really are equal. And either way, no matter how you do it, you end up with 340 as long as you had no calculation errors. Now, we already know going into this that we have K is equal to 4 and N is equal to 20, okay? So let's go ahead and calculate this bad boy out. Remember, this between subjects formula is going to work just like that between treatments formula did. So we'll take 88 squared divided by 4 plus 88 squared divided by 4 plus 60 squared divided by 4 plus 52 squared divided by 4 plus 52 squared divided by 4. And then we're going to subtract that G squared, sorry about that, that 340 squared divided by 20, okay? Now you're going to have to bear with me. I did not cheat and pre-calculate all this stuff for us, so I'm going to do that right now. So 88 squared is 7,744, and we get to use that one twice. 60 squared, oh, helps if I actually type 60, is 3,600, and 52 squared is 2,704. That 340 squared is equal to 15,600. Okay, so 115,600, and again, that's going to be divided by 20. Okay, so now let's do the math on all of these. 7,744 divided by 4 is equal to 1936. Helps when we have these same values. 3,600 divided by 4 is equal to 900, plus 2,704 divided by 4 is equal to 676. And we'll add those together. Okay, and we get a value of 6,024. When we take our 115,600 divided by 20, that gives us a value of 5,780. So 6,124 minus 5,780 is equal to 344. Okay, so that is our sums of squared between subjects is 344. Now that is the bulk of the math that you have to do for this second step. After this, it really becomes rather easy. Okay. So now we know, because we just calculated it, that our sums of squared between treatments is equal to 344. Our sums of squared within treatments we were given earlier is equal to 510. If we subtract those two, we get 168. So our sums of squared error is equal to 168. And this is what we'll use going on to calculate our ANOVA. Okay. So our sums of squared between treatments, we knew from before, and it was 840. Our degrees of freedom between treatments we calculated was 3. We'll do that math, and we get 280. We'll do the same thing for sums of squared error. We calculated our sums of squared error at 168. We calculated our degrees of freedom error at 12. We'll do the math on that, and we get 14. And so we take our mean squared between treatments. Let me undo that. Our mean squared between treatments of 280 divided by our mean squared error of 14, and we will get an F of 20. Yay! We did it. We made it. So that is our F value for this repeated measures ANOVA. Okay, so now we got to see, well, great, 20, that's awesome. But where does that line up? We are going to look up again our degrees of freedom numerator and our degrees of freedom denominator. So those are the two values that went in. So we used degrees of freedom between treatments, and we used degrees of freedom error. Okay, so degrees of freedom between treatments was 3. Degrees of freedom error was 12. Again, At 0.05, that will be 3.49. Our F of 20 is in that shaded area. It's in the critical region, so we are able to reject the null and support the research hypothesis.